All right, guys, going to go ahead and start talking about our semester final review. Okay, first question, it says calculate the density of a 23.412 gram object that occupies a 5.04 cubic centimeter space. Okay, on this question, we go ahead and we take it. We know that density equals mass divided by volume. We get this off of our formula chart. We go ahead and plug everything in. We have a mass of 23.412 grams, and we divide that by our 5.04 cubic centimeters. And guys, here you might get a little bit confused on the fact of you're thinking, hey, this is cubic centimeters. What does that mean? I thought centimeters was a length. But just remember that when we have cubic centimeters, that's length times width times height. So that's going to be volume. So all we got to do is divide those guys out. 0.4, and we get an answer of 4.645, which we could round that up to 4.65, and that's grams per cubic centimeter. Last thing, remember that cubic centimeters also equal 1 milliliter. Okay, guys, let's go ahead and start working this one out. And this one says, how many kilograms are there in 7,643 milligrams? Main thing here, we have to go from milligrams into kilograms, and we need a statement of equality. We know that 1 kilogram equals 1,000 grams, and 1,000 grams equals 1,000, or 1 gram equals 1,000 milligrams. Okay, so when we set it up, we always start with what the problem gives us. It gives us 7,643 milligrams, and we set up our boxes. Okay, remember, whatever's on top has got to go on bottom. So this is the one that says milligrams, so we put that on the bottom. 1,000 milligrams equals 1 gram. Now, we did not get it to our final unit of kilograms, so we got to keep going. And again, we look at it, whatever's on top has got to go on bottom. So we already used this, so we can't use it again. And we have that, which is 1,000 grams, and that unit matches up, equals 1 kilogram. And we go ahead and multiply the top and divide by the bottom, and we should get an answer of 0.007643. And that answer, since those units will cancel out as we go, will equal kilograms. Okay, guys, working the next one out, it says a volume is measured experimentally as 4.11 milliliters. What is the percent error given that the correct value is 4.11 milliliters? Now, main thing here that we got to remember is that percent error is the equation for it, okay, is going to be our measured minus our accepted all over our accepted times 100. We can find this on our formula chart, guys. Usually we take the absolute value of this just so that we don't get a negative value here. And our measured is what we always measure experimentally. And in this case, our measured is 4.11 minus our accepted, which accepted, another word for that is correct value. So 4.11 all divided by 4.11 times 100. Which we work this out, guys, and we'll see that we get 0 because we're just subtracting it right here. We get 0, and 0 divided by 4.11 would be 0 as well. So we have a 0% error. All right, guys, working out the next one. It says which of the properties, melting point, flammability, and density are chemical properties. Remember that chemical properties, when we measure them, it changes what that substance is. And when we look at the chemical properties, we can't record it or test it without changing it. Okay, so when we're looking at this, we see that we can look at the melting point of ice, and we see when ice melts, and it's still water. It hasn't changed, so this is not a chemical property. Okay, we look at flammability. If we were to test flammability, we'd have to light it on fire. So therefore it would change. So yes, that is a chemical property. And then we look at density. Well, we can look at density. Density is mass divided by volume. Well, we can measure the volume and we can measure the mass without changing what it is. So that is not So the correct answer would be just only 2. All right, guys, on this one we are looking at, it says which of the following is correct. And we're looking at elements, and we see that we have nonmetals, metals, and some metalloids. So we got to figure out where they are on the periodic table. Now remember, we have the stair step that runs down our periodic table. When we say that everything to the right of the stair step is going to be a nonmetal and everything to the left is going to be a metal. So it says calcium is a nonmetal. Calcium is right here. It's obviously to the left. That's not correct. Okay, it says radon is a metal. Radon is right here, and it's to the right of the periodic table, and that is not correct. Then it says sulfur is a nonmetal. Sulfur is right here. Yes, that would be correct because it is a nonmetal. It's to the right of the stair step. See that silicon, no, that's not going to be a metal either. It's to the right. And then sodium way over here says it was a metalloid way over here, and that's not correct either. So the only correct answer is sulfur. It's to the right of the stair step. It is a nonmetal. All right, guys, working number 13 out. It says how many protons are there in a nitrogen 15? Okay, so it gave us the 15. Think of it as being up here. Gave us the hyphen notation. But when we're looking at it, it says how many protons are there in an atom of nitrogen. Well, we know that this number that comes after it, that's our mass number. That's the number of protons plus neutrons. So we don't want that. But it did tell us that it is nitrogen. And we know that we can look at an element on the periodic table. And if we know the element, we look above it. And there's always going to tell us the atomic number. And the atomic number always represents the number of protons. So we look on the periodic table. We look above the symbol and see that nitrogen has 7 protons. All right, guys, working this one out, it says suppose that a hypothetical element consists of a mixture of 2 isotopes. So it tells us that we have 2 isotopes. Okay, and it says that one isotope having the mass of 44 AMUs is present in 27% abundance, while the other is having 46 AMUs, accounts for the other 72.3%. What should be the experimentally determined atomic weight for this hypothetical element? Whenever we're finding atomic weight or atomic mass, all we do is we multiply the percent by the AMU and we add them up. So what we should get is we should get 44 AMUs times 27.7, which would give us 12.188, and then 46 times 72.3, which would give us 33.258. We add both of those guys up, and we should get an answer of 45.446, and that would be AMUs. All right, guys, in this question it says how many moles are in 4.53 times 10 to the 23rd atoms. Okay, so we're doing some conversion factor here. The conversion factor that we need to remember is 1 mole equals 6.022 times 10 to the 23rd atoms. Okay, so when we set this up, we set it up with what the problem gives us. It gives us 4.53 times 10 to the 23rd atoms of fluorine. Remember, this can be atoms of anything on the periodic table. In this case, it's just fluorine. Okay, so we set it up, and remember, whatever's on top's got to go on bottom. So we're going to put this on bottom, which is 6.022 times 10 to the 23rd atoms on the bottom, and it equals 1 mole. So all we do is multiply the top, which is 4.53 times 10 to the 23rd, times 1, all divided by 6.022 times 10 to the 23rd, and we should get an answer of right around 0.752242, and that would be moles. Okay, guys, looking at this one, it says, what is the mass of 22 moles of the element nickel? Okay, the conversion factor here that we're going to use is we know that 1 mole of anything, in this case nickel, equals its molar mass. And since it's just nickel, it's what the number on the periodic table. So nickel's molar mass is 58.0 0.93, and we'll just round it at that. Okay, that's grams of nickel. Okay, so it wants to know the mass, which is grams, so we got the molar mass. So the next thing we do is we set it up, and we start with what the problem gives us. It gives us 22 moles of nickel. Start with what we got, and remember, whatever's on top has got to go on bottom. So moles of nickel, we see moles of nickel right there, so we put 1 mole of nickel, and then we put our 58.93 grams of nickel on top, and we multiply 22.2 times 58.93, and we should get an answer right around 1302.92 grams. Okay, on this one it says determine the mass of 3.18 times 10 to the 23rd atoms. So we're going from atoms to mass, so we're going to need 2 conversion factors on this one. Okay, our 2 conversion factors, we know that 1 mole of anything equals 6.022 times 10 to the 23rd atoms. We also know that 1 mole of anything equals the molar mass. And in this case, we're dealing with chlorine, which chlorine is going to be 35.45 grams. We found this on the periodic table. So all we got to do is set up our problem. We take it, and we take our 3.18 times 10 to the 23rd atoms on the top. And these have to match, so we put atoms on the bottom, the 6.022 times 10 to the 23rd atoms equals 1 mole. Set that up, and since we have mole on top right here, we go ahead and use this conversion factor because we can't use that one, we already used it. So 1 mole on the bottom equals 35.45 grams of chlorine. And then we just multiply the top out, so 3.18 times 10 to the 23rd times 1 times 35.45, and we get that answer. And then we divide that by 6.022 times 10 to the 23rd times 1, and we should get an answer right around 18.7199. In the unit, we see that it cancels as we go. It's going to be grams of chlorine. Okay guys, here on this question it says what is the correct electron configuration for magnesium? So we're looking for magnesium, and we see that it's over here on the periodic table. Now remember, when we're doing the electron configurations, that it's broken up into our blocks. We have our S block. Down here we have our D block. Here we have our P block. And then usually below us on the lanthanide and actinide series we have our F block. But here we're only going to magnesium. We don't involve the F block at all. So we're just going to use the condensed version of the periodic table. Remember, all we do is we just start counting. Remember that this is 1, so 1s, 1, 2. Okay, so 1s2. Then we're done with that row. We come over here, 2s, 1, 2. Okay, so 2s2. Keep following the row. And we have, this is 2, but it's a different block. It's P, so it's 2P, 1, 2, 3, 4, 5, 6. So 2P6. Start over here. This is 3, 3s, 1, 2. We made it to magnesium. So this would be magnesium's electron configuration. Alright guys, on this one it says write the electron dot notation for the element phosphorus. Okay, remember when we're representing the electron dot notation, what it represents is the valence electrons. Okay, so all we do is we draw the symbol, and then we're going to put the valence electrons around it. So we look at phosphorus, and phosphorus is on the periodic table, and it is in group 15. Okay, and it's in group 15, so it has 5 valence electrons. Okay, so I need 5 dots around phosphorus. So I go ahead and draw these, and I get 1, 2, 3, 4, and 5. Remember, put 2 at the top, and then spread them out. All right, guys, on this one it says complete the nuclear equation. Now, when we're looking at nuclear, there's a couple things we have to remember. Remember that in a nuclear reaction, we're going to have the splitting or breaking off of elements. And basically what's happening is we're affecting the nucleus of a particular element. So what we have to see is that when we're looking in these equations, the numbers on top on both sides have to add up to be the same. So we kind of draw a line down the middle and we say that on this side, the mass number on top is 218. So over here, we have to have 218. Okay? But we already have 4. So 218 minus 4, that means that the number on here is going to be 214. Okay? Now, remember that the bottom numbers, the atomic numbers, also have to match. So over here we have a total of 84. Well, over here we need 84. So we already have 2, so 84 minus 2 is going to give me 82. And then since this is the atomic number, I look on the periodic table, I find 82, and I write down its symbol. And this is what would complete that nuclear reaction. Okay, guys, on this one it says, what is the frequency of a radio wave with an energy of 4.604 times 10 to the negative 24th joules per photon? Now, when we're looking at this, it tells us that we have an energy. Okay? Anytime it's talking about energy or wavelength or frequency, we're always going to use these two equations, where we have energy equals Planck's constant times frequency, and speed of light equals wavelength times frequency. Remember that wavelength has to be in meters. Okay, but this one's talking about energy, and it's talking about frequency. So if it talks about energy and frequency, we're going to use our first equation, where we have energy equals our frequency times Planck's constant. Now, Planck's constant is 6.63 times 10 to the negative 34th. Okay? And it's times frequency, which is that. And it's asking us for the frequency. Okay? So we can go ahead and we can plug in our energy, where we're going to have this equation, 4.604 times 10 to the 24th, and that would be negative 24th, equals our Planck's constant, 6.63 times 10 to the negative 34th, times our frequency. So to solve for frequency, we divide both sides by 6.63 times 10 to the negative 34th. We cancel these guys out. That goes to 0, and we get a frequency, and our answer should be, or actually that goes to 1, not 0, but our frequency should be 6.948 times 10 to the 9th hertz. Alright, guys, on this one it says which diagram 1, 2, 3, or 4 best characterizes a mixture. When we're looking at this, the main thing we have to remember is what is a mixture. Well, a mixture is going to be either more than one atom in the same place that aren't bonded together, or it's going to be a compound and atoms in the same place not bonded together, or a two compounds in the same place. Okay, so in looking at this, we see that this is going to be a pure substance because it's just one compound. Same thing here, a very pure substance. When we're looking at this, we see that here we have an atom and then a compound here. That would be characterized as a mixture. So the first two, definitely not. They're pure substances. But number 3, yes, that would be a mixture. And then we look at the last one, and we see that we have two compounds in the same place. So that is a mixture as well. So the answer should be number 3 and number 4. Okay, guys, looking at this one, it says identify the incorrect statement regarding Dalton's atomic theory. It said number 1, all matter is composed of atoms. Well, Dalton said that. That is correct, so it's not incorrect. Number 2, it says a given compound always has the same relative number of types of atoms. Dalton said that as well. That is correct as well. And then number 3, that all atoms of a given element are identical. Okay, and Dalton said that as well, and yes, that was in his theory. And then we see number 4 is that all matter is composed of protons, electrons, and neutrons, and that is not correct. That was not in Dalton's atomic theory. He did not state that there was anything smaller than protons, or wasn't anything smaller than an atom. Didn't even state about protons, electrons, or neutrons. This one, it says, what is the order of increasing atomic radius? Remember that atomic radius is always going to increase as we go that way. So increasing means from smallest to largest, and we have chlorine, we have sulfur, and silicon. So correctly, they're going to increase as they go this way, which increasing means going from smallest to largest. So increasing from chlorine, sulfur to silicon, which the correct answer should be number 1, chlorine, sulfur, silicon. All right, guys, looking at this one, we are looking at the problem. It says the electronegativity of an atom generally blanks going down the columns and blank going left across the periodic table. Well, we know that it increases as it gets closer to fluorine. So if it's going down the columns, obviously we know that it is going to be decreasing. Okay, so anything that says increasing, we can mark that out. Definitely not. It's going to be decreasing. Okay, and then it says going from left to right across the period. So going this way, we see that it is going to be increasing because it's getting closer towards fluorine. Okay, so we're down to this one right here, and we know that an element like fluorine will most likely form a covalent bond. We know that it's going to be covalent because a non-metal forming a bond with carbon, so it's going to be a covalent bond. All right, guys, moving on from here to the next question. It says the elements to the left of the dark line on the periodic table are, and the correct answer should be metals. Metals are always located to the left of the stair step. Non-metals are to the right. Key concept that we need to have down, especially when we start talking about ionic and covalent bonding, because we got to know the difference between a metal and a non-metal. All right, guys, moving on to the next one. It says use electron dot notation to demonstrate the formation of an ionic compound involving sodium and sulfur. Okay, now main thing that we have to know here, it tells us that we have an ionic compound. On our test, it might not tell us that we have an ionic compound, so we have to know that this sodium is to the left of the stair step, so it's a metal, and sulfur is a non-metal. So at any time we have a metal-non-metal bond, we're going to have an ionic. Anytime we make the formula for ionic compounds, we are always going to crisscross. And we're going to crisscross their oxidation numbers. Okay, so we need to know what their oxidation numbers are. Now, remember that the oxidation numbers follow the hill of oxidation numbers. We've talked about this. Remember we said that group 1 has a +1 oxidation number, 2 is +2, then we jump to 13 is +3, 14 is going to be plus or minus 4, and then 15 is -3, 16 is -2, and 17 is -1. And this is our hill of oxidation numbers, and these are just their group numbers, the columns on the periodic table. Okay, so once we know it's ionic, we know that we're going to crisscross, so we got to find their oxidation number. So we go ahead, we look over here, and we look on our periodic table, and we know that sodium is going to be in group 1. So I know that's going to have a +1 oxidation number. And then I know that sulfur is going to be in group 16, so it's going to have a -2 oxidation number. Now, here we just take them and we crisscross. Now, the signs are not important when we make the formula. We just bring down the numbers. We bring down the 2 and we bring down the 1. So we get Na2S1, which we just leave the 1 off. So this is our formula that we're looking for. Now, the plus, the positive, and the negatives, those come into play because those tell us what's happening to the electrons. So in sodium, its electron dot is going to be just 1 dot. Okay, it's Na, it's +1, has 1 dot. And then sulfur, when looking at its dot, it has 6 valence electrons. Okay, and it's -2. So what happens is we have to have 2 sodiums giving one of their electrons to sulfur to make this compound. So we would look for the Lewis structure that looks like this, or we would look for the electron dot structure that looks like this, which we would have the sodium giving one to the one sodium giving each of their electron to sulfur. Okay, so our answer is going to be a combination of this formula plus this electron dot. Main thing here, make sure you remember that electron dots, those are valence electrons, and then our formulas, those are oxidation numbers. All right, guys, moving on to the next one. It says name the compound SNO. Now, the first thing we have to know in any time we're naming a compound is we have to figure out, is it ionic, is it covalent, or is it an acid? Okay. Now, there's one way that we can tell this. We always look at the very first element in the formula, which we have to figure out if it's a metal, is it a hydrogen, or is it a non-metal. If it's a metal, we know that it's ionic. If it's hydrogen, we know that it's an acid. And if it's a non-metal, we know that it's going to be covalent. Okay, so we look at 10. 10 is to the left of the stair step, so I know that Sn is a metal. So I know that this is going to be an ionic compound. Okay, so we have SNO. Now, it's very simple when we name an ionic compound. The very first part is just going to be 10. Okay, so we can start off and we see that, yep, all of them have 10, so all of these choices are right. Okay, the next thing we have to look at, is that metal a D block metal? Is it in group 3 through 12? Now, we're going to treat this, even though 10 is not in the D block, we're going to treat it as a D block metal. Okay, you won't get any of these exceptions on your test. You would just get D block metals. Okay, but we're going to pretend, just for example's sake, that 10 is a D block metal. Okay, so we have 10, and oxygen would be oxide. Now, the trick here is, since 10 is a D block metal, it has to have a Roman numeral. Okay, anytime you have a D block metal, it has to be a Roman numeral. So you can automatically just look at our answers, and that's not right, that's not right, and that's not right, because it doesn't have a Roman numeral. Now, the Roman numeral, remember, it only goes for D block metals. So we have two options. We have 10-2 oxide or 10-1 oxide. Now, to tell this, we're going to do our right triangle rule. Okay, now remember, on our right triangle rule, the first thing we do is we find the oxidation number of oxygen, and all we care about is the number. Well, oxygen is in group 16, so it has a -2 oxidation number. Okay, and we compare that to the subscript of 10, which it is a 1 because it didn't have a subscript. Okay, so if it does not match, what we're going to do is take the subscript of oxygen, which is a 1 because it didn't have one, and multiply. Okay, remember, we don't worry about the sign. So 1 times 2 equals 2. Okay, so that means that my answer is going to be 10-2 oxide. Okay, the reason why I picked it is because they did not match, so I multiply the subscript and the oxidation number. Okay, if they did match, which this is just another example, say we had SN2O like that. Okay, well, we look at the oxidation number of oxygen, it's 2. Well, if they did match, that would be the oxidation number. Okay, so yes, they did. Okay, guys, moving on to the next one. Now here, it says name the compound NO2. Now the first thing we have to do in naming any compound is we have to tell, is it ionic, is it covalent, or is it an acid? Okay, now to do that, we look at the very first element in the compound. Okay, if it's a metal, we know that it's ionic. If it's a non-metal, we know that it's covalent. If it starts with an H, we know that it's an acid. Okay, so we look at this and we see that it's an N, and we see that N stands for nitrogen, which we know nitrogen is a non-metal because it's to the right of the stair step on the periodic table. Anytime we are naming a covalent compound, we are always using the Greek prefix system. Okay, so we can look at here, and anything that doesn't have a prefix, meaning mono, di, tri, tetrapenta, hexahepta, octa, nanodeca, we can go ahead and rule out. So nitrogen 4-oxide, definitely not. Nitrogen dioxide, we can leave that one in there. Nitrate is a polyatomic, nitrite is a polyatomic, and then we have nitrogen oxide, which it doesn't have a prefix either. So the only answer that could be right is number 2. It's nitrogen dioxide. Okay, we only have one nitrogen, so that's correct. We just write nitrogen. And then we have 2 oxygens, and that is where we get the dioxide from. So the correct answer should be number 2. Okay, guys, moving on to the next one. We see that it says name the compound HNO3. So we got to figure it out. Acid, base, or sorry, is it an acid? Is it an ionic compound or covalent compound? It begins with an H, so we know that it's an acid. So we look at it, and when we name an acid, we have to decide, hey, is it binary or is it a ternary acid? If it's hydrogen and one other thing, it's binary. But we see that we have hydrogen, nitrogen, oxygen. So that means everything after hydrogen is going to be a polyatomic, which we know that NO3, if we look on our chart, is going to be nitrate. Okay, and the rules for naming ternary acids, if it ends in ATE, we erase that. We put IC and then acid. So this should be nitric acid, which we look down and we see, there it is, nitric acid. So number 6 would be the correct answer. Okay, guys, working this one out. It says salicylic acid used in the synthesis of aspirin has a composition of, we see it as 60.08% carbon, 4.38% hydrogen, and 34.75% oxygen. What is the empirical formula for the compound? Now, when solving for the empirical formula, all we do is we take our percent, which 60.87, and we have 4.38, and then lastly we have 34.75. We take those guys, and what we're going to start by doing is dividing them by their molar mass to get them into moles. Okay, we're going to pretend that these, instead of percents, we're just going to change them to grams. Okay, so we're going to divide by their molar mass. Now we know that carbon has a molar mass of 12.01 equals 1 mole. Hydrogen is 1.01 equals 1 mole. And oxygen is 16.00 equals 1 mole. So we go ahead and we plug these guys into the calculator, and we go ahead and divide those out. And for our carbon, we see that we are going to have an answer of 5.06, and that would be moles. And then for hydrogen, we would have our 4.33, and that's moles. And then for oxygen, we have 2.17 moles. Now all we do from here is once we calculate the moles, the next step is we divide by the lowest number, which the lowest number is 2.17. So we divide everything by 2.17. And we get our next answer. And our next answer is going to be 2.33 for carbon. 1.995, which we're going to go ahead and round to 2, because we round the thousandth place. And if we round from the thousandth place, it goes to 2. And then lastly, when we divide it by itself, we get 1. So we get these 3 numbers. And these are going to be our subscripts for carbon and this is hydrogen and this is oxygen. But the thing is, we cannot have a 0.33. We have to have a whole number. Okay? So here, 2 is a whole number, 1's a whole number, so we really have to think of what do we multiply 2.33 by to get a whole number. And when we do that, if we multiply 2.33 times, we go ahead and multiply it by 2, and we see we get 4.66. Well, that wouldn't work. Okay, so 2 is not the answer, so we go 2.33 times 3, and we see that we get 6.99, which 6.99 is close enough to round to 7. So if we multiply it by 3, we get 7. We multiply 2 by 3, and we get 6. And multiply 1 by 3, and we get 3. Okay, these are our whole numbers that we're going to use. So all we do is it's going to be C7H6O3, and that is going to be our empirical formula. All right, guys, moving on. It says determine the molecular formula of a compound with an empirical formula of CH and a formula mass of 78.11 AMUs. Now, with this, since it's given us an empirical formula, it's pretty easy. All we have to do is given us the formula mass, which we know that that's the mass of the formula, the molecular formula. So all we have to do is find the mass of the empirical formula. So we have carbon and hydrogen. We have 1 of each of them. We multiply them by their atomic masses. And we see once we multiply them by their atomic masses and add them up, we are going to get 13.01 grams. Well, that is the mass of the empirical formula. So all we do is we take the 78.110 AMUs, divide it by the empirical formula mass, which is 13.01 grams, and we see that we would get 6. And we multiply that 6 by all the subscripts in our empirical formula. So we only have one carbon, so it turns to C6. One hydrogen, H6. So this would be our molecular formula. All right, guys. Now it says an alkene has a molecular formula of C12H24, and it said determine the percent composition. Whenever we're determining the percent composition, we're going to do that by mass. Okay, so in our equation we have carbon, we have hydrogen, we have 12 carbons and 24 hydrogens, and all we do is we multiply them by their atomic masses. So carbon is going to be 12.01 and hydrogen is going to be 1.01. And we are going to get those of 144.12 and 24.24. Then all we do is our next step is we just add them up to get a total of 168.36. And then all we do is we come back and we divide each of them by the total. 168.36, 168.36. We divide those guys out and we would get a percent. And remember, once we divide them, we multiply them by 100, we get a percent, and we would get 85.6 for carbon, and we would get 14.4 for hydrogen.